Self-attention mechanism, the foundation of Q, K, V. The word lock doesn't know whether it belongs on a door or on a hilltop. For a model operating on static vectors, both meanings are identical. The same point in space, the same representation, zero context. That's only the beginning of the problem. In the sentence, the robot lifted the heavy block because it was strong, the word it refers to the robot, not to the block. A human understands this instantly. A static embedding doesn't encode that. Every occurrence of the word it gets the same vector, regardless of context, regardless of sentence, regardless of meaning. For an architect working with RAG systems, the consequences are direct. A model operating on static embeddings returns irrelevant chunks because it can't distinguish the contextual usage of words. The problem is fundamental, and in 2017, a team of 8 researchers proposed a solution, primarily from Google Brain and Google Research, with participation from the University of Toronto. The paper, "Attention is All You Need," has been cited over 173,000 times. It's one of the 10 most cited scientific papers of the 21st century. Notably, all 8 authors eventually left Google. 3 specialized vector projections, query, key, and value, transform isolated embeddings into context-aware representations. 3 simple matrix multiplications that gave machines context. Today, I break down that formula into 4 steps. After this episode, you'll understand why self-attention needs 3 separate projections and how the scaled dot-product attention formula works. Three specializations in one mechanism. Every effective project team has specialists. One member asks questions and defines needs, the analyst. Another evaluates how well skills match requirements, the recruiter. A third delivers concrete results, the executor. The self-attention mechanism discovered the same principle. For every token in a sequence, the model creates 3 separate vectors, each with a different function. Query, the analyst. The query vector defines what a given token is looking for in context. It's the analyst formulating a precise request. I need information about the subject of this sentence. Technically, Q is the result of multiplying the token embedding by the learned weight matrix WQ. The matrix WQ transforms the raw embedding into a search perspective. Key, the recruiter. The key vector describes what a given token offers to other tokens. It's a competency label, a recruiter with a business card. I'm a noun in the subject role. Key is produced by multiplying by the matrix WK. Key and query must have the same dimension DK, because they'll be compared via dot product. This dimensional constraint is fundamental. Value, the executor. The value vector holds the content that the token actually delivers, the concrete knowledge and skills the executor brings to the project. Value is produced by multiplying by the matrix WV. The dimension of value can be anything. What we deliver doesn't need to have the same shape as how we search. Think about it. The query has a different format than the answer. In attention, it's exactly the same. 3 weight matrices, WQ, WK, and WV, are learned during training. The model discovers on its own which projections are most useful for a given task. WQ can learn to extract syntactic features. WK can advertise grammatical role. WV can store semantic information. 3 independent transformations of the same embedding, each specialized in a different aspect. When you're debugging a model or analyzing attention weights, you see exactly these 3 perspectives in action. The answer to how these 3 roles collaborate is contained in one elegant formula. The formula that changed everything. Part 1. The full power of self-attention is contained in one formula. Attention of QKV equals softmax of Q times K transposed divided by the square root of D minus K times V. 4 steps, from dot product through scaling and softmax to weighted sum, Step 1. Dot product Q times K transposed. The first operation computes a compatibility measure between tokens. The query of one token is dot multiplied against the key of every other token. The larger the dot product, the more relevant those tokens are to each other. In team terms, the analyst checks which recruiter has the best competency match. The result is an n by n matrix, every token compared against every other. Step 2. Scaling by the square root of d minus k. Without scaling, the dot product grows proportionally to the vector dimension. For d minus k equal to 64, values can exceed 30 or 40. This pushes softmax into a region of very small gradients. Dividing by the square root of d minus k restores variance to approximately 1, regardless of dimension. This is numerical stabilization. It prevents softmax saturation and blocks gradients from vanishing during training. For d my model equal to 512 with 8 heads, d minus k is 64, so we scale by 8. The formula that changed everything. Part 2. Step 3. Softmax. The scaled scores pass through the softmax function, which normalizes them to a probability distribution. The sum of weights for each query equals 1. All values are non-negative. Each word gets an attention budget to distribute among the other words in the sequence. A word strongly aligned with the query gets a high weight. An irrelevant word gets a weight close to 0. Step 4. Weighted sum of values. The final step multiplies the attention weights by the value matrix. The result is a new vector for each token, a contextually aware representation. The word lock in the context lock on the door gets a representation enriched with information from the tokens on and door. The same word in the context lock on the hill gets an entirely different representation. The problem of static embeddings. Solved. Let's see this in concrete numbers. The sentence cat sits, dimension d equal to 2, instead of 512 in practice. The weight matrices are simplified. The mechanism works identically to a full dimensional model. After computing q, k, and v for both tokens, the dot product yields an attention scores matrix. We scale by the square root of 2, that gives approximately 1.41. After softmax, the token sits gets weights, 0.31 for cat and 0.69 for sits. This means the token sits allocates 31% of its attention to the word cat. The resulting vector for sits incorporates information from cat, weighted by that value. The model knows who sits. That's contextual awareness in action. The formula is elegant. 4 steps from a simple dot product to a contextual representation of every token. One fundamental question remains. Why 3 separate matrices, not 1? The answer to what would happen if q, k, and v were the same vector, that's exactly what the next chapter explains. Why 3 roles, not 1? This is the pivotal moment of the entire episode. The separation of q, k, v isn't accidental. It's a deliberate architectural decision with deep consequences. Suppose q equals k equals v equals x. The model uses raw embeddings without separate projections. The formula simplifies to softmax of x times x transposed divided by the square root of d minus k times x. This still works. It's mathematically valid. The model loses flexibility, however. It can no longer separately control 2 fundamentally different operations: how we search for similarities between tokens and what content we pass forward. In practice, the performance degradation is significant, especially on language tasks. The asymmetry of roles is the key to understanding. What you're looking for, query, isn't the same as what you offer, key, or what you pass along, value. A verb as a query might search for a subject in the key role. What it passes forward as a value is semantic information about the action. 3 different operations on the same data, each specialized. Think of it in team terms. If one person in a company simultaneously acted as analyst, recruiter, and executor, the team would perform worse. Not because that person is incompetent, because 3 different perspectives require 3 different ways of looking at the same data. Specialization is the key to flexibility. That's precisely why self-attention needs 3 separate weight matrices. That's precisely why this mechanism works so well. This isn't abstraction, it's an architectural tool. When you design a system with cross-attention, for example in multimodal RAG, this separation gives you control. Query comes from one source, keys from another. One mechanism, three roles, global context. Global, meaning every token sees every other. That feature has its price. The price of global context. Self-attention compares every token against every other. That delivers global context, but at a concrete cost. Multiplying the matrix Q times K transposed requires operations on an n by d minus k matrix and a d minus k by n matrix. The result is an n by n matrix. Computational complexity, O of n squared times d model. Memory complexity, O of n squared. Doubling the sequence length quadruples the cost of attention. That's the quadratic nature of the operation, and it's exactly what limits the context window in standard implementations. Concrete numbers. For a sentence of 100 tokens with d model equal to 512, self-attention requires approximately 5.1 million operations, all in parallel. RNN needs approximately 26 million, more than 5 times as many. That's not the end of it, however. RNN executes 100 sequential steps, one after another, token by token, no parallelization. Attention executes all operations in parallel on the GPU. In real time, it runs many times faster than sequential RNN. The trade-off is clear. Attention delivers full parallelization. The GPU processes the entire sequence at once. RNN processes token by token. Attention provides direct access to all tokens. Every word sees every other word. RNN relies on short-term memory that fades in long sequences. In the first episode, we discussed how Polish has more tokens than English. More tokens, higher attention cost, growing quadratically. That's one of the reasons a prompt in Polish costs more to process than an equivalent prompt in English. Flash attention, sparse attention, sliding window, these are active research areas aimed at reducing that cost. Each approach limits quadratic complexity while preserving the contextual power of the mechanism. Self-attention has its price. That price is worth paying. One mechanism, free roles, global context. Self-attention transforms isolated embeddings into context-aware representations. It does this through free specialized projections. Query defines what the token is looking for in context. Key describes what the token offers to other tokens. Value holds the content the token actually delivers. The scaled dot-product attention formula realizes this collaboration in 4 steps. The dot product measures compatibility. Scaling stabilizes numerically. Softmax normalizes to a probability distribution. The weighted sum delivers the contextual representation. Every step has a precise rationale. The separation of Q, K, V is the foundation of this architecture. If Q equaled K and V, the model would lose the flexibility to independently control how to search for similarities and what to pass forward. 3 independent weight matrices give the model the specialization that a single shared representation can't provide. Quadratic complexity, O of n squared, is the price of global context. Parallelization on the GPU makes that price worth paying. Attention runs many times faster than sequential RNN in practice. When you see D model equal to 512, 8 heads, dk equal to 64 in a model configuration, now you understand why those numbers matter. When you see a longer prompt processing more slowly, you understand the quadratic nature of the problem. The next step is running many such mechanisms in parallel, each with a different specialization. One mechanism will capture syntactic relationships, another semantic, another positional. That's multi-head attention, the topic of the next episode. If this episode helped you understand self-attention, Subscribe to the channel and leave a comment with a question. Next episode, multi-head attention. We'll see what happens when you run many of these teams in parallel. One mechanism, 3 roles, global context. See you in the next episode.